Hey guys, here's a coding question from Google. So you're given a binary tree um, where the value at each node is a number between 1 and n. So here we can see it's 1, 2, 3, 4, 5, all the way up to 11. Um, and we're also given a list of queries. So the input is this list of queries, and it is also this tree, this binary tree. And the whole point of this problem is for each query, for example, for this first query, for this value, we want to return, or we want to store the height of the tree if the height of the tree at this node if this 3 node was removed. So for example, this first query is saying, so if node 3 is removed, if this entire section is taken off, then what is the height of our remaining tree? So it's 1, 2, 3, right? 3 edges. So that's a height of 3. And then same thing for 6. If you remove 6, so you remove this section, then we end up with also a height of 3. And so basically, we have a bunch of values to query, and we store all of the answers in their respective indices. So how would you sort of approach this problem? We want to be able to return, or we want to be able to do each query very quickly, right? We don't want each query to take very long. If we were to do a very naive approach and we actually removed each block and then reiterated through the entire tree, that would cause runtime to be very high because we have to reiterate this entire block again. So we have to find a way to sort of pre-process so that we can maybe figure out how tall the remainder of the tree is in O of 1, or maybe in logarithmic time. So how might we be able to do that? Well, first thing we want to be able to notice is that we can divide our tree into levels and heights. So we can see here I labeled that this 1 is at the 0th level, right? It's at the lowest level. And then this 2 and 3 is at 1, and then 2 and 3, 4, and so on and so forth. And then we can sort of notice that the height at each node is just the height of the path from any given node. For example, this path. If we were to look at 6, right? Let's say our query gives us 6. We would know that the height, the best path through 6 is just 6's level. So level of, so best height or best root height is equal to the level of that node plus the height of that node. So in this case, it's pretty intuitive, right? It's just saying this way, so these 2 lines plus these 2 lines gives us the total, the best root height, right? The best root height up here. So upon noticing that, we can see that we can use this information, and if we perform a sort of recursive pre-process in the beginning, what we can do is we can, before we even start performing any of the queries, we first iterate through all of the nodes and record the height of each node, and also record the level that that node is at, right? That way, we would know the best root height. But we're not done there, right? We have to remove that best root height. So let's say it's we're looking at this 7 query this time. If we're looking at 7, our best root height is going to be this entire path. So it's going to be 4. We can see that in this segment and this segment, right? But if we remove 7, there might be another height that is still equally as great. So what we can do is we can store another, we can store some more variables, and the other thing that we store is a mapping from a level to its 2 biggest heights. So the key is a level, and its value are the 2 biggest heights associated to that level. It's pretty intuitive, right? The thing is, if we take a look at this 6 or this 7, we see that there are three nodes at this level, right? We only need to keep track of the 2 nodes here that have the greatest height, right? Because after we remove the height associated with 7, we remove that path. Let's say that that path, in this case, let's say that that path is the longest path. Then we still have the second longest path. Then we just use the second longest path as our answer to our query. So for example here, we see there are 3 levels. If we, inside of our key value mapping, this level is at 3, and it would point to heights, the 2 biggest heights, and those are 0 and 1, right? So, because these both have 0, height 0, right? There's nothing underneath both of these nodes, and this one has 1. And once we see that this 7, because we also store this information up here, we see that its height is 1 and that its level is 3, we remove this one because this is no longer an option. And then we instantly know that our best height is just this one right here, because that was our next best one. Because for this level, this is the next best option. So we would know that our answer would just be 3 plus 0. So let's take a quick look at another example real quick. So another really good example that we should look at is this query at 8. Here, there's only one item in the mapping, right? At the level 4, there's only one height, and that is the one attributed to 8, and that's just 0. So if we remove 8, we once again look at the level, and then we see, okay, we got rid of this 0, because this is the path we just removed if we removed 8, right? We remove this path, which means we can say the 0 is gone. Now, there are no more nodes that reach this level. So instead, our answer would just be best root height is equal to level minus 1. So level of the node minus 1. Level node minus 1, right? Because if we remove this 8, and there are no more items that reach 8, that means we know that the next best height has to be 7, because we cut off here, we know that this height is going to be our best option, right? So it's basically, we put in 2 maximums two maximums for each level, and then when we query an item, we look at if the height of that item is one of the levels in our stored maximum, in our stored map. If it is, then we use the other one, the other item, that is the other height. So the other height plus the level will give us the total path. And that's sort of just like the intuition for how to do this problem.